In many cases, you'll be working with data in the form of a frequency distribution, which you'll either create from the data or you'll just interpret. This data set here shows a hospital with the various units, departments. And it looks like we've got the number of patients per department. To construct a frequency distribution, we simply take the frequency of each class. In this case, our classes are cardiac care, emergency care, intensive care, maternity, and surgery, and divide that by n. N would be the total number of patients in this example. So we would have to sum all of this data. And if you do that, you then take 1052 divided by the sum. That'll give you 0.12. That would be the relative frequency. Many cases, we want to state this as a percent. So we might say 0.12 relative frequency is actually a 12% frequency. And you'll notice if we do that for each of the units, we have a new way of interpreting the data. And this might be more useful. If you were doing a presentation as a hospital administrator, you're probably going to use percentages to display the different hospital units and illustrate the number of patients rather than the raw numbers. But it's up to the presenter, and this is one way to do it. Now, to get from the relative frequency of each class to the percent frequency, you just multiply by 100. So 0.12 times 100, move the decimal place 2 to the right, gives you 12%. In some cases, you'll find that the classes you're using are defined by a range of numbers. So here we've got the time in days to maybe complete a particular project, and it's 10 to 14, and then the next class is 15 to 19, that kind of thing. And then we have the frequency with which that's occurring. So it's a frequency distribution, just like before. We had the hospital units and then the number of patients in each unit that allowed us to determine the frequency distribution. Here we have time in days instead of hospital departments, but we still have the frequency, and we can use this data to determine the distribution. Many times when you're looking at data, you'll have a range. For example, before constructing this table here, the analyst probably saw that they have 10 days as the low end of their data set and 34 days as the high end. So before they constructed this table, they would have needed to determine how wide each of these classes needs to be in order to create the number of classes they want. To do that, the analyst would take the larger number and subtract the smaller number. So in this case, 34 is the largest number in our data set, 10 is the smallest number, so that gives us 24 as our numerator. We then would divide that by the number of classes that we want. So if this analyst says, well, I want, let's say, 3 classes, well, then you would take 24 and divide it by 3, and that means you would have a class width of 8. What if he says, as is the case, that he wants 1, 2, 3, 4, 5, 5 classes? Well, he would take 34 minus 10, which is 24, divided by 5. Now, the closest number you can get is going to be 25 divided by 5, and that's a class width of approximate 5. And that's what we have. Notice that time in days for the first class is 10, 11, 12, 13, 14. That's a width of 5. There's 5 days in that range. Then the second class is 15 to 19. Well, that's 15, 16, 17, 18, and 19. There's 5 there's 5 data points there, so on and so forth. So to find the approximate class width, just take your largest data minus your smallest data, and then divide it by the number of classes that you want, and you'll get an approximation of how many or how wide that class needs to be. You might also want to find the class midpoint. That is essentially the average in the data set. To do this, you take the largest data value, again 34, and you add the smallest data value, which is 10, that gives you 44. You then take 44 divided by 2, and that gives you 22. 22 would be the midpoint of our data. And notice that falls right here in between these two, which is perfect because it actually has 2 classes below, 2 classes above, and it's equidistant from the 2 data points within. Perfect midpoint. In some cases, you may want to create a cumulative frequency distribution. We have the same classes here and our frequencies, but maybe we want to find not the frequency of, say, 10 to 14 and then 15 to 19, but every number up to and including the respective class. For example, if we look at this is auditing time, it says, less than 14, then we would look at our data. We have 14. So that would essentially be all times up to 14 days. And that's a cumulative frequency of 4. If we want to look at less than or equal to 19, that includes our first 2 classes. So we would actually take the first class, 4, and add it to the second class, 8, giving us 12. If we want to look at less than or equal to 24, that would include the first class, the second class, and the class in question. We'd take 4 to 8 to 12, and we would end up with 17. And you just continue this process. Now, when you get to the highest value, you're going to have n, which is the total numbers of frequency in your data set. With this cumulative frequency, you can then create a relative frequency. Going back, we use the exact same formula. Relative frequency is the frequency of the class divided by n. Well, what's the frequency of this class here? 4 divided by 20, which is 0.2. What's the frequency of this class here? 12 divided by 20, which is 0.6, so on and so forth. You can then multiply your cumulative frequency by 100, just like we did back here, and get the actual percent. So we can then say that 85% of the observations were less than or equal to 24. That kind of thing. When presenting data, bar charts and histograms are very useful. Descriptive statistics is all about conveying information in a succinct but effective way. And while frequency tables are useful, people tend to connect more with charts. If we take the data from our prior example with the hospital, we had constructed the relative and percent frequency distribution. We can convert this into a bar chart. So if we do that, we have cardiac care, emergency care, intensive care, maternity, and surgery on the horizontal axis, and then we have the actual numbers presented here. So it's much easier now to see how surgery dominates everything else and how intensive care is the lowest. If you want to convert a bar chart into a histogram, then you simply get rid of the gaps between the bars. And this is not always appropriate, especially when it comes to categorical data. Cardiac care and emergency care, having the space between there divides them in a neat and logical way. But if you have ranges of numbers, like we saw with the days, 1 to 5, 6 to 10, 11 to 15, that kind of thing, then you may want to get rid of those gaps because you have a continuum. 1 to 5 doesn't have a gap when the next bar is 6 to 10, and there shouldn't be a gap there when the next bar is 11 to 15. So a histogram is really just acknowledging that there are no natural gaps between bars when you have a continuum of numbers. So to summarize, use a histogram when you do have a continuum of numbers, and use a bar chart without or with the gaps when you're using non-numerical data. Pie charts are another way to convey data and can be very useful when you're dealing with percentages that sum to 100. For example, here we've got our hospital unit again, and we simply take the percentages that we calculated before for each class and we convert it into a pie chart. And you get good information in a succinct way. Again, you can see surgery dominates and intensive care is tiny. But unlike the bar chart, the pie chart actually shows us that we're breaking down a whole hospital. Line charts and scatter plots are also useful for communicating data. Here we've got a time series data of number of park visitors per year, and you can take the data points for different years here and connect them with a line, and you can start to see a trend. Looks like an increase in number of park visitors. Scatter plots are useful for correlating data. That's where you take two variables and plot them in a graph. This looks like we're looking at price on the vertical and quality on the horizontal, and then each of these might represent a specific data point. And perhaps this is a particular product, and we're trying to see if the increased quality correlates with higher price. Might be good for a business to know that if they make quality improvements, will they be able to charge more? Later on in the regression section, you'll see that there's ways to actually draw a line and determine if there is in fact a correlation between two variables. That's in essence what regression is. And so you can kind of see an upward trend here. So this data suggests that price and quality are positively correlated.